Okay, so we are going to be looking at method of differences, which is the first half of chapter 2. The second half of chapter 2 is Maclaurin expansions, and they are pretty different. And we're just going to kind of dive in with these. They are building on the series that we did in year 1 further maths, but they're not the same thing. The only thing that's the same is what the notation will look like. So all the sigma notation is going to be coming up again. So in order to explore method of differences, I am just going to be thinking about a couple of things here, just to kind of get us in the mode of what we might be able to do. This is not really going to be to do with method of differences directly, but it's going to start getting us to think about ways of making complex things looking more simple. What do you think we can do for this long multiplication that I've got at the top that might make us be able to calculate what's actually happening in this calculation? Can you see anything that's happening here that I could do to simplify this long calculation? We could use factorials, but I think factorials may end up making this more complex. I'm just wondering if there's anything you can spot when you're multiplying fractions, what you're usually allowed to do when you're multiplying fractions. Ishak? Yeah, look, there's loads of numerators and denominators that are matching. So I could cancel this 2 with this 2, this 3 with this 3. Will the 4 cancel out with something? Yeah, the 4 will. What would cancel out of these bits that we've got here? The n minus 1 would cancel. Because if you look at the pattern, it's this one, the bottom one, leaving the top one, and so those two match, those two match. So there would be an n minus 1 down here as well that would have cancelled out with the n minus 1 if we continued this geometric series that we've got here. A geometric series is where they're being multiplied rather than added. And so what does this all simplify to? 1 over n. So this whole thing simplifies to 1 over n. This isn't the same as method of differences, but do you see there's that shortcut of being able to cancel things out? That is what's going to happen for the theme of this topic. There's going to be shortcuts of complex things cancelling out and getting more simple. And this one's not so obvious. There doesn't appear to be anything that cancels right away. This time the geometric series, I've got 1 minus 1 over a quarter, 1 minus 1 over 9, and to the end of it, it's 1 minus 1 over n squared. I didn't start with 1 minus 1 over 1 squared. I only started with 1 minus 1 over 2 squared. Why wouldn't I start with this one? Because it'd be 0, and the whole thing would equal 0, because you're multiplying by 0. So what do you think I could do for this series that I've got here? Or not this geometric series. What do you think I could do, like an algebraic technique that might be able to get something to pop up? Could you expand out? It would be very long if we expanded out all these brackets here.
I see you could write out the first few terms and then see if you can cancel anything and split that.
Okay, so do you mean like start expanding the first few brackets?
I mean that, so do 1 minus a quarter and then do 1 minus 1 over 9.
Okay, so that's one of the things we could try. 1 minus a quarter is? And 1 minus a ninth? 8 over 9, 1 minus a 16th, 15 over 16. I don't think there looks like anything that obvious that's happening there. So I want to go back to this and I want to think of another algebraic technique that I might be able to do to these brackets. If I showed you this bracket, what do you think I'm trying to get you to do to this bracket? A bracket with two things and a subtraction in the middle. Difference of 2 squares, okay? So we're going to I'm just showing you that there's weird things that can happen to try and simplify stuff like this. So I'm going to write them all as a difference of 2 squares, and we'll see what happens. So what would 1 minus a quarter be? 1 plus a half. I'm actually going to do it 1 minus a half, 1 plus a half, I think. Let me check in a second. 1 minus a half, 1 plus a half. And then this bit would be 1 minus a third, 1 plus a third, 1 minus a quarter, 1 plus a quarter, etc. And then our last one would be 1 minus 1 over n, 1 plus 1 over n. Okay, so 1 minus a half is a half, 1 plus a half is, and then I've got 1 minus a third, that's 2 over 3, multiplied by 4 over 3, multiplied by 3 over 4 multiplied by 5 over 4 multiplied by dot, dot, dot. What would this be if I added those together? N minus 1 over n multiplied by n plus 1 over n. Can you see anything that's happening here? You get a lot of pairs cancelling out here. So the 3 and the 3 cancels, and the 2 and the 2 cancels. The 4 and the 4 cancel, the 3 and the 3 cancel. Although you can't see it, the 5 and the 4 will cancel as well. And so will these ones as well. So the only one that we have is the 1 minus a half at the beginning, and at the end, the 1 plus 1 over n. 1 plus 1 over n. So when this whole thing, I should have really put a couple of equal signs in here to show that this is all going to be the same. So we've just got a half times n plus 1 over n, which is just n plus 1 over 2n. So this idea is like, let's just explore and see what happens and see if we can get lots of things cancelling out. That's going to be like the main theme that we have here for method of differences. How can we get all of these things to cancel out? And these are geometric series. You won't have to do these kinds of problems, but I wanted to start the lesson off with these problems to get us into the right mode of thinking, okay? So this is what method of differences is actually going to be like, okay? This is a proper method of differences question. And we're going to explore what happens for this series that we've got here. And I'm sure you remember what all of the notation actually means. So I've said here, hint, perhaps write out the first few terms to see what is actually going to happen when we do this particular series that we've got here. So we're going to use those ideas from that start of the lesson to see how we might be able to work this one out. Now, you obviously couldn't use your year 12 technique for this because we don't know what the sum of 1 over r is, and we don't know what the sum of 1 over r plus 1 is. All we know is the sum of r squared, and r cubed. Yeah? So I'm going to just start substituting in some numbers. I'm going to start off by substituting in r equals 1, which would give me 1 over 1 minus 1 over 2. Then I'm going to substitute in r equals 2. And I like to write it on the next line, and you'll see why I like to write it on the next line in the future, okay? But rather than writing it in a long list, I just like to write it underneath. So when I substitute in 2, I will have 1 over 2 minus 1 over 3. And when I substitute in 3, I would have 1 over 3 minus 1 over 4. And I'll do one more. If I substitute in 4, I would have 1 over 4 minus 1 over 5. And this would keep going and keep going and keep going. So I'll put plus dot, dot, dot. And then what I'm going to do is just finish off with the last couple of ones that we would have. So the penultimate one would be n minus 1. So I would have 1 over n minus 1 minus 1 over n. And then my ultimate one, my last one, is n, which would be 1 over n minus 1 over n plus 1. So I'm just going to quickly jot down here. This was when r equals 1. This was when r equals 2. When r equals 3. When r is equal to 4. When r is the penultimate one. And when r is the last one that we've got here. So using that information we had from the beginning of the lesson, what do you think you can see happening? Can anybody spot what's happening here? What cancels? Yeah. This plus half and this minus half cancels. This plus third minus third cancels. This plus quarter minus quarter cancels. Something down here is going to cancel with the fifth, and this one will cancel, and you can also see these ones cancelling that we've got here as well. So the entire series is equal to 1 over 1 minus 1 over n plus 1. It's pretty cool, isn't it, how the function behaves in such a way that it all collapses down and you just get 1 over n minus 1. I'm just going to combine these together. So that would be n plus 1 minus 1 over n plus 1, which is just n over n plus 1. And that's a kind of intro to what method of differences actually looks like. That's a method of differences question in its kind of most simplistic kind of form. You've got all of those things cancelling. And we need to think about why it is called method of differences. Well, the word difference means subtraction. So there's got to be a subtraction in it, because if there wasn't a subtraction, you'd never have these things cancelling out from each other, right? So the next thing I wanted to have a look at is to kind of generalize this. Because if we can generalize this, this will allow us to access some of the much more challenging questions. The only exam question that they've done on this didn't follow the pattern that we're going to do in today's lesson. It didn't follow the pattern that we're going to do on next lesson I see you after half term. It followed something different, and knowing this technique would allow you to kind of spot that pattern a little bit better. So here, did everybody get that all written down? Did anybody need a bit more time on here? So here it just says, if un equals f of n minus f of n plus 1, then this thing here is true. This is known as the method of differences, but I want to break this all down a little bit more, okay? Un, this just means, this means the term in the nth position. This means it's the term in the nth position. I don't know why they use the letter u. Normally we would have done this in pure maths before this, but we just haven't done series. If you want to look at series from the pure maths videos, you can do as well. So it's, pardon? There is series in maths as well, yeah. But you don't, it doesn't actually link to any of the stuff in further maths apart from the sigma notation. So this means the term in the nth position. Let me just make that a little bit clearer, because that looks like it was all blending in the nth position. So if the nth term of something is in the form f of n minus f of n plus 1, and I think our previous one that we had, we said it was 1 over r minus 1 over r plus 1, like this. So we're actually saying that u of n is equal to 1 over n minus 1 over n plus 1. Yep, that's all we're saying. That's the nth term that goes into the series that we've got here. So in this particular case, if we're saying it's in this form, which it is in this form, what is f of n in this particular case that we've got here? Just comparing this to the statement that we've got at the top. It's just 1 over n. And then that's good, because the next bit that we've got of here, f of n plus 1, is 1 over n plus 1. So it is in the form of f of n minus f of n plus 1. Just because if we can use this function notation, it will save us often having to write down absolutely everything that's there. So if we're going to do the sum from r equals 1 to n of u r, because we're substituting r in these different places here, well, we know if it's in this form that it has, it would be substituting in 1. So it would be f of 1 minus f of 2. Do you see how I'm substituting in 1 to both of them for the first line? So I have f of 1 minus f of 2. Then when I substitute in 2, I would have f of 2 minus f of 3. And then I would have f of 3 minus f of 4. I'm going to put plus dot dot dot. And then I would have f of n minus 1 minus f of n plus f of n minus f of n plus 1. So that's exactly what we just did on the previous page, but I'm doing the whole thing using function notation. And as I said, the reason I'm using that function notation is to prepare you for some of the more challenging questions that are usually not covered in the teaching of this, okay? And then they decided to do this weird exam question, which obviously we'll do in a few lessons' time. And this technique is a useful way of exploring that. So do you see what we did? We took the question that we had, we established that it was in that form, and the function was 1 over n, and it was subtracting 1 over the function, it was subtracting the function of n plus 1. Now if you see all of these things that we've got here, it becomes really clear to see that the f of 2 and the f of 2 here, they cancel. These cancel. Those would have cancelled, those would have cancelled, and that cancels. So you can see now how it's coming up with that we have f of 1 minus f of n plus 1. Now, I probably would still recommend... Oh, hang on a sec. Oh, yeah, I've done that right, sorry. I probably still would recommend writing them out like this manually and seeing what happens when things cross out, especially in today's first lesson. But it's important that at the start of this, I also want to show you what it looks like with the function notation so that you can reach those top-level questions, just in case they decide to do something with a bit of a twist, where this might be something that's helpful. So if we look back at what our question was, we said that f of n was 1 over n. So if we're going to say the sum from r equals 1 to n of 1 over r minus 1 over r plus 1, using this, it's just the function where 1 is put in, 1 over 1, minus the function where n plus 1 is put in. So it would just be 1 over n plus 1, which is the same thing that we had before, which came out as n over n plus 1. So if you can recognize that, then you could use this particular formula, but I don't advise that at this point. But what I do advise is being able to write things in function notation because it allows you to spot the patterns easier than spotting the patterns with numbers. Okay, we're going to do one example, and then we'll do a few practice questions, and then we'll come back and do some more examples as well. Everyone got all this down? Okay, so it says, first of all, show that 4r cubed is equal to this thing that we've got on the right-hand side. And then it says, prove by the method of differences that the sum of r cubed from r equals 1 to n is a quarter n squared, n plus 1 squared. Have we ever seen any of that stuff before that's there? Yeah, where? It's year 1, isn't it? Do you remember I told you, did I teach you series? I think I did. That I told you, I was like, oh, this is just the formula for r cubed. But now actually we can prove that this is the formula for r cubed rather than just having to trust me that it is the formula for r cubed. And I've said here for the exam note that exam questions usually will have two parts here. They will have the first part will usually show that some expression is equivalent to one of the form of f of n minus f of n plus 1, because that's what we just talked about on the previous page. And then the second part is actually to use the method of differences to simplify the summation that we've got there. So I'm going to start off, if I call this beginning part A and then this second part here B, I'm going to start off by trying to show that this thing is true. So which side do you want to work on, left-hand side or right-hand side? Of course we want to work on the right-hand side because the left-hand side is so simple. So we've got r squared, r plus 1 squared, minus r minus 1 squared, r squared. And we're literally just going to work through multiplying everything out there. So r squared multiplied by r plus 1 squared. R plus 1 squared is r squared plus 2r plus 1. And then we're going to minus r minus 1 squared, which is r squared minus 2r plus 1, multiplied by r squared. It'll probably be easier if you just do this yourself, and then just look up and check you've got the same thing as me. So I've got r to the 4 plus 2r cubed plus r squared minus r to the 4 plus 2r cubed minus r squared. Cancels and cancels. And I have r cubed. Pardon? That's it. It's just a simple thing to begin with. That part A is either going to be like an algebraic manipulation or it might be partial fractions that we'll have a look at in the next example anyway. So we've now done this. We've shown that it's equal to 4r cubed. And the next thing it wants us to do is prove by the method of differences that the sum from r equals 1 to n of r cubed is the thing that we already know about. But I'm not going to do r cubed. Instead, if I work out the sum of 4r cubed, because I already know what 4r cubed is equal to. So I'm going to work out the sum of 4r cubed, and then at the end, I will just divide it by 4. Okay? There's obviously you could do it. You could find out what r cubed is and just keep the quarter in there if you wanted to. But I just prefer to put the 4 outside the front. So the sum of 4r cubed is actually just going to be equal to the sum from r equals 1 to n. I'm going to replace, this whole thing is 4r cubed. So I'm going to replace this with the expression that they just said was the same as 4r cubed. So I'm incorporating the 4 in, and I'm just going to write it as r squared, r plus 1 squared, minus r minus 1 squared, r squared, close brackets, like this. And then I'm going to do the manual method of differences, and then afterwards I'm going to show you what we did with the function notation, because I want to try and skill you up at both things. I personally would do the manual method, but then if I had a difficult question, I would do the function one. So you'll have to try and look at both. Okay, so we're just going to start substituting things in and see what happens here. Now, if I substitute in r equals 1, I would have 1 squared times 2 squared minus, well, that would just be 0 squared times 1 squared that I've got there. Now, for the next bit, I'm going to substitute in 2. So I would have 2 squared times 3 squared, and I would subtract 1 squared times 2 squared. And then for the next one that I would have, I'm going to substitute in 3. So that's 3 squared times 4 squared minus 2 squared times 3 squared, like this. And to write the next line, you can often see what the pattern is. So if I was going to do the next one, it goes 1, 2, 3, it's going to be a 4, 2, 3, 4, it's going to be a 5, 0, 1, 2, it's going to be a 3, 1, 2, 3, it's going to be a 4. But I'm just going to miss out a couple of them. So I'm going to go to the, you don't have to do this penultimate one, but I quite like doing the penultimate one. So I'm going to do n minus 1. So that would be an n minus 1 squared. N minus 1 plus 1 is just n, so it's n squared. Then it's going to be n minus 1 minus 1, which is n minus 2 squared, n minus 1 squared. And then my last line, when n is equal to 1, it's n squared, n plus 1 squared, minus n minus 1 squared, n squared. So you may like to jot down, that's when r is 1, 2, and 3, when it's the penultimate one, and when it's the last one that we've got there. How do they cancel this time? The first one goes with this one here. This one goes with this one here. This one would go with one down here. So always doing that pattern, that. Which tells me, if I rewrite what I've got here, that 4 of the sum of r cubed is equal to n squared brackets n plus 1 squared minus 0 squared times 1 squared, n squared n plus 1 squared minus 0 squared times 1 squared, which is obviously just going to be 0. And so the sum from r equals 1 to n of r cubed is a quarter n squared n plus 1 squared. Now the crossing out pattern in this one was different from the crossing out pattern in the first one. Do you see the difference when you look at the two questions? What was different about the crossing out pattern?
This time we read it left to right, and last time we read right to the left.
Yeah, look, in the previous one that we had here, we had the starting one, and then the last one was left. The top left and the bottom right. In this one, the ones that we've got left over are the top right and the bottom left. So I want to say, why is that? Why did that happen? What do you mean, Sam? Okay, good. So usually we were talking about, this is now we're going to start exploring the function notation for this question. We said if it's in the form of f of n minus f of n plus 1, then the sum was equal to f of 1 minus f of n plus 1. But in this case, our one seems to have come out a bit different. It looks like we've got f of n minus, hang on a sec, f of n. Yeah, our one has come up with f of n minus f of 1. Is that f of n or f of n plus 1? Yeah, our one's come out a bit different for this one, for our sum of r cubed. It's the other way round. We want to just have a quick think about why that has happened by using some function notation. So, this is tricky, this bit. The main thing I need you to take away is just how to do this, but as ever, I'm always trying to prep you for the hardest things that could be there, and so this function notation is going to be interesting. So, let's just think about this thing that I've got here. I have, well, the board's got a bit crazy, a bit glitchy. I've got r squared, r plus 1 squared, minus r minus 1 squared, r squared. What do we think that if we were trying to put it in this notation, what is f of n in this case that we've got? No, I don't agree. If we were trying to put it in this notation that we've got. Because if this was n, in the next one, they've decreased here. Pardon? No, you've got to have a look at the whole expression that you've got.
It will be the right-hand side, so a minus.
Yeah. This is what I would call f of n. So I would say that f of n was equal to... I'm going to leave the minus for a second. I would say it is n minus 1 squared, n squared. And then f of n plus 1, well, if I change that from an n, if I substitute n plus 1 in here, I would have n squared, don't need the bracket, and then n plus 1 squared that I've got here. So the question that I was doing wasn't of that form. In fact, if we're doing it this way round, our function that we were doing was of the form this one, which is f of n plus 1 minus f of n. Do you see how that's actually what our one is in the structure of? Our one has this equation that we were summing up was of the form f of n plus 1 minus f of n, which is slightly different to what we said the general form looked like, because the general form we said was f of n minus f of n plus 1, so it's the other way round. So we can just see how this would behave by substituting in values. So if I substituted in values that we've got here, for n equals 1, we would have f of 2 minus f of 1. For n equals 2, we would have f of 3 minus f of 2. Then we would have f of 4 minus f of 3, etc. And then at the end, when I substitute in n minus 1, I would have f of n minus f of n minus 1. And then when I substitute in n, I would have f of n plus 1 minus f of n. So the things that should be cancelling here is this one. So you get that one cancelling, that one cancelling, that one cancelling, and that one cancelling, which is why we get left with f of n plus 1 minus f of 1, which tells me I've actually done this wrong at the top here, that our one wasn't f of n. It was actually f of n plus 1 because of the way we defined f of n as n minus 1 n minus 1 squared n squared. And this is definitely more complicated for what I'm saying here, but I wanted to show you this, that you can decide what you think the function is that they've got in common, and then you can explore it using function notation, because sometimes it's going to be easier to use it in exploring in function notation. But for the questions I'm going to ask you to do, I don't want you to do it this way. I want you to do it this way first of all, and then try and think about how would it look in function notation. This one is weird because it's reversed. And I guess the reason it's reversed is because normally it's that one minus that one, so it's been negated. So the answer has also been negated here as well. And the negation of what that looks like in the crossing off patterns is that you get different bits remaining at the end. You get the opposite bits remaining. So I'm going to get us to do a few practice questions. Then we'll do some partial fractions questions. and then we'll finish up this first half of it. So the function notation is there to kind of deepen the understanding, to see how these things cross out, but it's a pretty tricky example that we've got there. Okay.